Good afternoon. We have talked about TCP congestion control last time. We'll revise it quickly and then continue with the advanced algorithms. So initially, we said that sender's window of the TCP, which decides the segments which we can send at a time, and then we'll have to stop the transmission. That is dependent on two parameters: network's capacity and receiver's capacity. Whichever is minimum, based on that, transmitter's flow has to be tuned. Receiver's capacity is reported to us in the header in the field of window size. However, we cannot know the exact network capacity. However, we can try to estimate that. And that estimation is probed in the parameter called congestion window. So, most of the time in the real-time situation, receiver's window would be larger than congestion window. So we can say that the sender's window would be decided based on the congestion window. However, keep in mind that in case receiver's window is smaller than congestion window, then your sender's window will be restricted by that. But in general, whatever is the value of the congestion window, that would be the effective value of the sender's window. This is what we have talked about. Are you with me? So initially, when we start transmission over a connection, we would not know the network capacity. So we start from the small value, that is 1, and then we send that data. After 1 RTT, if everything is well, we will get an acknowledgement. And when you get an acknowledgement, you double the window. You send 2 packets, 2 segments. After 1 RTT, 1 round trip time, under normal circumstances, you will get 2 acknowledgements. Then we'll make it 4. That is what we have talked about. So after each RTT, your congestion window will be doubled. This is the phase which is known as slow start or exponential increase, because exponentially we are increasing the window. So every RTT, congestion window is being doubled. And it is also known as acknowledgement clocking, because when the acknowledgement comes, then our window is incremented. So here actually when you send 1 acknowledgement, then after 1 acknowledgement, it will be incremented by 1. So if you send 4, let us say congestion window is 4. So we have sent 4 segments. So when you get 4 acknowledgements, then you will not actually wait for 4 acknowledgements and then make it double. On arrival of each acknowledgement, you will make it 1, 5, 6, 7, and 8, and so on. So when the congestion window value is n, you are expecting n acknowledgements. On arrival of each acknowledgement, it is incremented by 1. So it will be incremented by n. And effectively, it will be 2n when you get all the acknowledgements back. This is how it is implemented. So it is acknowledgement tuned. On arrival of acknowledgement, your congestion window will be incremented by 1. In case of slow start, which is also known as exponential increase. Now we know that initially that is okay to make it from 2 to 4 and 4 to 8 and probably from 8 to 16, 16 to 32 and so on. But once the value is pretty large, like 256, then if our network could carry 256 segments, then to assume that it will be able to also carry 512 segments is pretty unrealistic. And by chance, if it would carry 512 segments, then next time around 1000 segments, then we are bound to collapse the network. So we need to be cautious and we enter in the linear rise after encountering slow start threshold. So once the threshold is encountered, we enter in the linear rise. In the linear rise, we are increasing our congestion window in the linear fashion. It is also known as additive increase, or it is also known as congestion avoidance, because we try to avoid the congestion by entering in the linear rise. So here, if we assume that initially the linear rise is being followed, then congestion window is 1. Then after 1 RTT, when you get all the acknowledgements, which is 1 acknowledgement, we'll make it 2. Then when you get 2 acknowledgements back, then after 2 acknowledgements, we'll make it 3. Then when you're getting 3 acknowledgements, then you will make it 4. So effective increase in the congestion window is 1 after every RTT. So if I have to tell you that actually in the implementation it is not so, it will not wait for all the acknowledgements to come and then it will be incrementing by 1. It will not do that. Can you give me the equation that what would be implemented for the additive increase? Like here in slow start, increment congestion window by 1 for each acknowledgement. So if acknowledgement arrives, make congestion window plus 1. That is the equation. What about this one? In additive increase, on arrival of each acknowledgement, by what amount should you increase the congestion window? Not by 1. Okay, well, if we increment by 1, that means here we have sent 3, congestion window is 3. So we have sent 3 segments on arrival of each acknowledgement. If we increment it by 1, then it will be 4, 5 and 6. That means it will be 6 after this RTT. If you increment congestion window by 1 on arrival of each acknowledgement. So can anyone tell me? What do you mean by previous acknowledgements plus 1 channel? Let us say we are at this stage. Congestion window is 1. 3. Sorry, at this one where the cursor is. The congestion window is 3. So in the normal circumstances, I'll be getting 3 acknowledgements. 2 times we sent means and say after, yes, Prince, after each RTT congestion window will be congestion window plus 1. That is true. Yes. But I want to see the growth in rate on arrival of each acknowledgement. Then what would it be? We cannot have burden of remembering number of RTTs. In C channel, if there was a case of, let us say, timeout, then after timeout we know that we retune the parameters and then again we begin. So actual number of RTTs which has passed in this particular connection could be different, isn't it? Isn't this pretty simple? Like if congestion window is 3, then on arrival of each acknowledgement, you will be incrementing it by 1 by 3. So 1 by 3 plus 1 by 3 plus 1 by 3. So effectively, on arrival of all the acknowledgements, we are going to make it incremented by 1. Do I make sense to you? Pretty simple, isn't it, Kaval? Yes, everyone. Prince, Priyank. So this is what will be done. So we don't need to remember the number of RTTs passed or how many acknowledgements have come and then we increment it. Rather, directly based on the acknowledgement and the current value of congestion window, this is how we tune it. And why do we do it? Because here it was 4. Then after all the acknowledgements, suddenly if you make it 8, then there will be sudden increase and 4 packet you will be sending on the network together. While here on arrival of acknowledgement, if you increment it slowly and if the congestion window allows, then smoothly packet will be sent over the network rather than being concentrated. That is why we make it dependent on the acknowledgements. So it's 1 on every RTT, but actually this is what will be followed. So if the congestion window value is 3.4, then you will be sending 3 segments only. If it is 3.7, you will be sending 3 segments only. The moment it is 4.2, something like that, then you will be sending 4 segments. So initially slow start, then linear rise or additive increase or congestion avoidance is the other name. And this is what we do. Once the threshold is encountered, we enter in the linear rise or additive increase. Whenever there is a packet loss, then whatever was the value of congestion window, let us say congestion window was 40 kb. In this example, at this point, when the loss was encountered, at that time, the congestion window was 40 kb. Then we are making our threshold 20 kb. And our congestion window value will be 1. And from 1, it will be 2, 4, 8, 16 and so on. At 20, again, we will stop the slow start or let us say exponential increase, and we will be cautious. This is what is being followed. It is also known as additive increase, multiple decrease. AIMD algorithm is a term which is vastly used for this because we are slowly adding up, but whenever there is a timeout, then multiple RTTs which were lapsed in probing it, we are decrementing that. So this is another name. Now last time, threshold value. What is the congestion window value at the time of packet loss? It is 40. So half of that is how it is 20. Here it is assumed that one packet is of 1 kilobytes. Okay. So it is KB or number of segments. In this particular figure, it is given that one segment or one packet is of 1 kilobytes. Okay. Any other doubts? Anyone? Feel free to ask me as and when you have doubts. Everyone, are we on the same page? So now we said that because our network could not deliver one more segment, that is not very wise to punish it by reducing it to 1. You raised that right concern last time as well. So apart from that, another concern which we might think about is like you have sent the data and now there will be timeout after some time. That is round trip time. Round trip time plus some additional time like queuing delay, processing delay, and some extra buffer would be there. So there are many algorithms. One of them is Jacobson algorithm, which is used to tune the timeout. So we are having two parameters which might affect the performance. One, waiting duration for the timeout. You exploited the window, we have sent based on the congestion window those many segments, and then we have to stop the transmission. And because acknowledgement is not going to come to you because the packet is dropped or it is erroneous. In any case, let us say you have sent packet number 21 to 50. 21 to 50 you have sent. Now if 21 is dropped, then receiver, if it is getting 22, 23, 24 and so on, it will buffer them out of order because we are following selective repeat. However, acknowledgement would not be generated. Acknowledgement will not be generated. So here at the transmitter, after sending 21 to 50, we are waiting and we are not doing any transmission. So we are idle waiting for some acknowledgement to arrive or timeout to take place. Because when the timeout takes place, then only 21 can be retransmitted. So there is something called duplicate acknowledgement. Like receiver has received 20 successfully. 20th segment is delivered successfully. Let me write it. Then what acknowledgement would be generated by the receiver? If yes, we are assuming here that one segment is of 1 byte to make it simple. Ideally, if the 20th segment is there, and if there are 100 bytes, then 20 to 119, those many say bytes would be delivered and will be getting acknowledgement of 121. But to make it simple, we are assuming that each segment is numbered and accordingly we send it. Now let us say 21st segment, as we have talked, is dropped. Now receiver receives 22nd segment. So in this case, receiver would not send any acknowledgement because 22nd segment it is getting. It will store it temporarily. However, there is nothing wrong in sending the acknowledgement of 21. But we had already sent acknowledgement of 21. So this is known as duplicate acknowledgement because we are sending it once again. So this is duplicate acknowledgement of 21. Now we are getting 23rd segment. Again, 22nd hasn't come yet. So we can again send duplicate acknowledgement of 21. So this is second duplicate acknowledgement which we are sending. This is first duplicate acknowledgement. This is second duplicate acknowledgement. When you are getting 24th, then Again, receiver will be sending the same acknowledgement, which is third duplicate acknowledgement, and so on. So I hope you understand that whenever receiver is getting correct data in order, then appropriate acknowledgement will be sent. However, if it is getting data out of order, we can always issue duplicate acknowledgements. There is no harm in that. So whenever your transmitter receives 3 duplicate acknowledgements, then transmitter will be attempting retransmission of that suspected dropped segment, which is known as fast retransmission. Fast retransmission of 21st in this case. Why? Because transmitter thinks like this. It has sent 20th, it has got acknowledgement of that, so up to 20 everything was fine. Now it is getting duplicate acknowledgement of 21, another duplicate acknowledgement of 21, yet another duplicate acknowledgement of 21. So there are at least 3 segments which were sent after 21, and they are successfully delivered at the transmission at the receiver. So even if another path was taken, then 21st would have made it by now. If 21st is not reaching there, 21 segment is not reaching there, and there were 3 segments which were generated after that. If they are reaching there, then there is a high possibility that due to congestion or some other reason, 21 is dropped. And if it is dropped, then rather than attempting retransmission after timeout, it is better to retransmit it earlier, so that progress will be done and recovery will be faster, efficiency will be better. So it will not wait for timeout of 21. It will be sending 21 right after 3 duplicate acknowledgements. Now why 3? Why not 2 or 4? They have performed experiments and figured out that 3 is a decent count, that by 3 if it is not delivered, it will not be delivered. That is what they have experienced so far. Like, we cannot be hurry and send it right after 1 duplicate acknowledgement or 2 duplicate acknowledgements, because by chance if it is taken another path which might be slightly longer, then we are provoking unnecessary retransmission. And we don't need to make the threshold more than 3 duplicate acknowledgements, because they have observed in general that if it is not delivered within 3, that will not be delivered even afterwards. So now you have learned just one more term, fast retransmission. Fast retransmission will be attempted whenever receiver generates 3 duplicate acknowledgement of the same number, the transmitter receives them, then without waiting for retransmission timeout or RTO, it will be retransmitting this. And apart from whenever fast retransmission is done, it knows that now it was the case of loss. So there was the case could be of the congestion, and it will be reducing your congestion window to half. Your congestion window and slow start threshold, both of them would be reduced to the half of the recent congestion window. So this algorithm which I have talked earlier, whenever there is a timeout, then congestion window will be 1 and threshold will be half. That is part of the Tahoe TCP or the basic TCP. While fast retransmission, and this is known as a part of fast recovery, that is attempted in Reno TCP and new Reno TCP as well. Subsequently, there was one fine change done in new Reno TCP, which you don't need to worry about at the moment. Just remember that in the Reno TCP, we have concepts of fast retransmission and fast recovery. Why fast recovery? Because in the earlier scenario, whenever we said that there was a timeout, then it could be a case of loss. And if it is a case of loss, we were reducing our congestion window to 1. Now, rather than keeping it 1, we are making it half. So, quickly, we will recover from this episode of the loss. And we will try to match the actual congestion window, which it should be based on the current network capacity. If it was 1, then certainly we will be taking more time to probe it. While if it is half, then in the lesser time, fast, quickly, we will be able to recover from the impact of the loss. So have you understood fast retransmission and fast recovery? Okay, a nice one. So what Dev is asking is, if 23rd is also dropped. Okay, what Dev is saying that let us take another scenario. According to Dev's 21 is dropped, 23rd is dropped. So in this scenario, duplicate acknowledgement for 23rd will not be sent. When 24th is received, then we'll be getting acknowledgement of this only. Now, when 25th is delivered, packet number 25, then it will be generating acknowledgement of 21. So transmitter actually doesn't know that 23 is dropped. It is getting acknowledgement of 21, 21, 21. So what it will do? It will fast transmit 21. It will send faster transmission of 21. And now this 21 will be received by the receiver. So what will receiver do? If it is successfully delivered, then can you tell me what will receiver do? Yes, it will send the acknowledgement of 23. Yes, it will send the acknowledgement of 23. Now let us say on the network, now we know that 21 has been delivered, 22 has been delivered. So if your transmitter is having the space and receiver is allowing that, then you will be sending more segments. So when 25th is received by the receiver, then receiver will be generating duplicate acknowledgement of 23. When 27th is delivered, then receiver will be generating duplicate acknowledgement of 23, and so on. So when 3 duplicate acknowledgement of 23 are available, then 23rd will be retransmitted. Fast retransmission of 23 will be done. Otherwise, it will not be attempted. So actually, I'm not getting into minute details of, like you said that here we have actually 2 cases of losses. Multiple losses are there in the same window. And they were not very easily attempted in case of Reno TCP. I said that there was Reno TCP. Where did I say that? Yes. And that is why in the new Reno TCP, they have attempted this also by the concept of partial acknowledgement. Partial acknowledgement is something like this, which I have talked about without naming it. So anyway, Dev, have I answered your question? Did you get it? Okay. So others, feel free to ask me if you have any doubts, or is this clear? Okay, so now I have a question. Let us say our congestion window is 3 as of now, or let us say congestion window is 4. If congestion window is 4, then if one packet is dropped, then you will get 3 duplicate acknowledgements and we will be able to attempt faster transmission. But however, as they've said that if 2 segments are dropped, my congestion window is 4 and 2 segments are dropped. So maximum number of duplicate acknowledgements which will be generated, how many of them would be there? Your congestion window or sender's window is 4. And out of these 4 segments which we have sent, 2 of them are dropped. Then what is the maximum number of duplicate acknowledgements generated by the receiver? 2, right? Because you have sent, let us say, 51, 52, 53 and 54. These 4 segments. Out of these 2 are dropped. 51 and 52, let us say. Then 53 and 54, 2 of them will be bringing the duplicate acknowledgements. Then our threshold of 3 duplicate acknowledgements is not matched, and fast retransmission will not be attempted. Do you agree with this? Then will we fail in this scenario? Will our TCP be unreliable here, or we have some alternate mechanism? Due to lack of sufficient number of duplicate acknowledgements, we are unable to go for fast transmission. Exactly, Priyank and Prince, yes. In this scenario, we have our old good mechanism of timeout. Then timeout will take place, and in due course of time, fast retransmission will be attempted and will be sending the data which was missing. So TCP will be reliable only. So fast retransmission is a mechanism on the top of RTO which enables a transmission to be made early to make it efficient. However, in some scenario, if it doesn't work, if it doesn't click, then we have timeout which will be taking care of that. But whenever there is a timeout, then congestion window will be 1. Whenever there is a fast transmission, then congestion window will be halved. Because we see that in case of fast transmission, if timeout is called, then there could be a severe case of congestion. Because another scenario could be you have sent the, like here 21 was dropped, then we have sent 21. But now if this retransmission is dropped, then there is no mechanism other than to depend on the timeout to attempt the retransmission. But in case of this, if the original packet is dropped, retransmission is also dropped, then we cannot rule out the congestion. Your network could be highly congested, and if that is the case, we would like to relieve our network from the congestion, and hence congestion window should be drastically reduced to 1. So let us summarize this very quickly. With fast recovery, which we get in the TCP new Reno, retransmit lost packet after 3 duplicate acknowledgements. No, not all the segments. No, Ronak. Only 21st will be sent. All others, we assume our receiver to store that. Because we are using selective repeat behavior in TCP. Like if TCP is getting correct segment, and if it is out of order, it will be stored at the transport layer. So you will be not sending that. You will just, it will just not go back in kind of scenario. So at receiver, yes, at the receiver, we have buffer. And in case if there was another gap, then accordingly we'll be getting the acknowledgement, and based on the acknowledgement, next can be sent. In Reno TCP, congestion possibility is less. How, Prince? No, yes, but why do you think that congestion would be lesser in case of Reno TCP? Why do you think that? Okay, would anyone like to answer this? Prince is asking that is there a possibility of less congestion in case of Reno TCP? What about others? What do you think? No. Yes. See why? Because congestion. Yes. Because see, what we are trying to do here is we are trying to attempt the fast recovery of the packets which have already been dropped. But congestion is dependent on the incoming capacity and outgoing capacity. So if router can forward n number of packets, but if it is getting more than n number of packets, then it will be facing the congestion. Now, who decides the incoming flow at the routers? Many users and many congestion. So you are just one of the transmitter who is sending the data. There are many parallel connections which are going on. So we don't know at what speed they are sending the data. So congestion is the cumulative impact of all the simultaneous flows. At the time of congestion, speed of transmission is not much reduced. Yes, it is not much reduced. But that we said that why we are not reducing that, right, Priyank? Because see, even if we were in the slow start, or even if it was in the linear rise, we are making it half because our network could carry half. So now, if it could carry, let us say at this point of time where my cursor is, if it is 15, now if it is 30, so if it cannot carry 30, then we can always go back to 15 because our network has carried that. If it fails to do so, then again we will be reducing it by half and so on. Yes, order of packet may change. That is why we have kept the duplicate acknowledgement threshold of 3 and not 1. Why will order of packet change? Like router is getting one segment, and while forwarding it knows that, okay, let us say we are having A, B, C, D. That is the path. So one router decides that let me send it to B. And now when the next segment arrives, at that time it is decided that now let me send it to C. So if B is of the shorter path, then C. No, wait. B is of the longer path and C is of the shorter path. Then the next one will be delivered more earlier than the previous one. So order of the packet at the transport layer may change. Yes. But however, this also theoretically we see that router will not be going to decide based on each segment. It will not be diverting that. It will be stable more of the time. We have contacted Geo people before last to last year, I guess. And we have asked them for the realistic scenario that how much time the packet flow would be changed in one connection. They said that around 95% of the time, the packets would be going through the same path, unless there is some drastic change, but then the new path will be followed. It is not so that it will not be moving in the pendulum fashion, like one segment on this path and the other segment on this path and again one on the third path and so on. It doesn't happen like that. Whichever path is better at that point of time, it will be there for a few seconds or a few minutes. So mostly all the segments of the same connection will be traveling through that path only, unless that path is either broken or a new better path is found. So if it is broken, then new path will be found and then all of them will be diverted through that only. Are you with me what I'm trying to convey you? Like theoretically we may say that each segment might be following different path of one segment, but that doesn't happen actually. Also 21st closed, then 22, 23, 24 transmit. See, yes, everyone be with me. Let us again attempt it. Okay. Our congestion window value would be something. Let us, our congestion window value is 10. If our congestion window value is 10, what is meaning of that? We have sent how many segments? We are allowed to send 10 segments. So we have sent 20, 21, 22, 23, 24, 5, 6, 7, 8 and 9. From 20 to 29 segments we are allowed to send. Are you with me? Up to everyone, please try to be with me. Okay, so now here 21st is dropped. So receiver has sent duplicate acknowledgement of this. On 25th will be delivered, 28th will be delivered, 29th will be delivered, and for all of this it will be sending this only. Now your transmitter has received 3 duplicate acknowledgements. So your transmitter is attempting fast transmission of 21. Now whenever 21 is delivered, your receiver has already stored 22, 23, 24, 5, 6, 7, 8 and 9 in the buffer temporarily at the transport layer. It is not delivered to the upper layer, it is stored at the transport layer. When 21 is delivered, if this was the only loss in the window, then it will issue acknowledgement of, can you tell me which acknowledgement would be sent by the receiver? 30, exactly, yes, that is true. And Kevin, yes. So 30 would be generated and we know that everything is done. So, okay, yes, you were trying to tell me that even if one of the packet is dropped, so it is out of order because retransmission is attempted. That is what you were suggesting? Yes, that is true. I was talking about out of ordering of data due to due to change in the path. Due to network layer or routing, it could be changed. I was trying to attempt that. So anyway, and see in this scenario, now let us take the example what Dev said, like 23rd was also dropped here, 23rd was also dropped here. In this scenario, what will happen, when we had 3 duplicate acknowledgements, we have retransmitted 21st. So what acknowledgement will be getting here if there were 2 packets dropped? Yes, you will get acknowledgement of 23. So when you get acknowledgement of 23, then you know that 21 has been delivered and 22 has been delivered. So you will try to send, let me make it, not 23. Let me not make it 23. But 25, just for my convenience here, and I want to avoid the corner cases, to make it quick. 25th is dropped. If 25th is dropped, then what acknowledgement will be getting? 25, because up to 24 everything has been delivered. In 25, acknowledgement will be getting. So when you get acknowledgement of 25, our congestion window is 10. So what will we do? We know that now 25, 6, 7, 8 and 9, those are outstanding. 1, 2, 3, 4 has been cleared. So now we are allowed to send 31, 32, 33 and 34. So when they are delivered at the receiver, then we are not going to get acknowledgement of 29 or 30, but we'll be getting the acknowledgement of 25, 25, 25, 25. So those are duplicate acknowledgements of 25. Once I have 3 duplicate acknowledgement of 25s, I'll be attempting retransmission of 25. And if everything is well, next time you will get acknowledgement of 34, because up to 33, everything is available at the receiver. Am I making this too complex, or you are with me? I didn't intend to go for multiple losses, but since you have raised it, I'm talking about this. Otherwise, just we are going to talk about the single loss in a window. But anyway, that was a nice question and we could deal with that. But if some of you didn't follow that, that is perfectly fine. If you just understood the concept of fast retransmission and fast recovery, that is sufficient for you. But because there was one question, I have just answered it. So I think everything is okay. And so now, for the multiple losses, there is one better mechanism as well, and the faster mechanism, which you said. Why I conveniently chose 25 and not 23 in this scenario? Because I wanted, 3 duplicate acknowledgements together, and then something like that. However, what you say 21 and 23 is also dropped, that is a realistic situation. For that, we have another version, which is Selective Acknowledgement Tcp or SEC TCP. So in Selective Acknowledgement TCP, apart from sending the duplicate acknowledgement, they use the options. In the option, they mention which packets it is having available with it. Let us say you have sent 1, 2, 3, 4, 5 and 6. These are the packets which you have sent. 2 is dropped, 3 and 5 is dropped. So when 1 is received, acknowledgement for 1 will be sent. This acknowledgement 1 means acknowledgement for this particular segment. Do not get into the fine details of the next byte, etc. So when this 1 is delivered, it sends acknowledgement of 1. Now 2 is not delivered, 3 is delivered. So what it does? It sends duplicate acknowledgement of 1, and in the selective acknowledgement, in the option, it writes that I am also having 3. When this 4 is delivered, it sends a duplicate acknowledgement of 3. But apart from that, in the SEC information, selective acknowledgement information, which is in the option, not in the compulsory header, it writes down 3, 4. Like I'm having 3 and 4. Now 5 is not delivered, 6 is available there. So in the normal scenario, if 6 was delivered, we will just be sending duplicate acknowledgement of 1. But here we are adding information like I'm having 3, 4 and I'm having 6. This is 3, 4 is known as one SEC block, selective acknowledgement block 1. This is another selective acknowledgement block 6. Now if 7 is delivered, we'll be writing something like this. Acknowledgement of 1, and in the SEC information, we are going to write 6, 7 and 3, 4. So you clearly know that this is acknowledgement of 1, 3 and 4 is delivered. That means 2 is yet to be delivered. And 5 is yet to be delivered. So you have kind of mirror image of what data your receiver is having. And accordingly, you can decide your retransmissions. So we will never have unnecessary or wrong retransmissions, and quick and efficient retransmissions will be supported in case of selective acknowledgements. So this is one of the options, selective acknowledgements, which is added along with new Reno, and this is implemented in Windows and Linux, both of that. Like there is support of selective acknowledgement by default unless we disable that. There is a provision to disable it, but if you don't do it, then selective acknowledgements are by default used because they facilitate deciding which packets are exactly delivered and which might be missing. Have you followed it? Yes. If 8 is also delivered, like after 7, 8 is also delivered, then it will be 6 to 8 and then 3, 4. If 9 is also delivered, then we will be changing this 6 to 9 and this. So this is one selective acknowledgement block. This is another selective acknowledgement block. And since you raised it, Yash, everyone, can you tell me that how many such blocks we can accommodate in TCP options? If there are no other options used, we are using all our options for the selective acknowledgements. Then how many such should we or would we be able to accommodate? If you think over that, then I think you should be able to answer it. Let me give you a hint. What is this 3 and this 9 or 4 or 6 for that matter? Which each one of this actually is? Yes, sequence number or acknowledgement number, right? Sequence number or acknowledgement number. How long is that? 32 bits. Now tell me. Wait, maximum how many options do you have? Maximum number of options, maximum bytes. $40 bytes, right? There are 40 bytes of the options. Now, if I say this is one selective acknowledgement block, it occupies two sequence numbers, the left edge and right edge of the sequence number, like starting from this to this, starting from 6 to 9, 6, 7, 8, 9. There is one sequence number to the second sequence number, something like this. So here 4 bytes and 4 bytes. 8 bytes are there in one sequence number, in one block. 8 bytes in one block, isn't it? Then how many maximum blocks can be there? How many such blocks can be there? Not 5. That was the expected answer initially from you, but actually 4 sec blocks will be there because we need to tell, like in the option, which type of option is this? This is selective acknowledgement option. This is maximum segment size option, MSS option. This is timestamp option. Code is there for each option, and we need to tell the receiver and transmitter that which option is used. Unless we tell them which option is used, we will not be able to decode what we are getting because eventually everything will be in the binary. So based on what option number is used, like if option number is 2, then it is X option. If it is X, option number is 3, then this is to be done. If it is 4, this is to be done, something like that. So some bytes or bits will be used to tell the transmitter and receiver that which type of option is that. And that will take some bytes away from the 40 bytes, and we will not be able to accommodate 4 or 5 sec blocks, but 4 sec blocks will be used. Are you with me? Like actually, Shefali madam has already talked in the network layer itself, the option and code numbers for each of the option. So similarly here, I'm not getting into details of that because that is just to remember that if this is the code, then this option is used. If this is the code, this option is used. Did you understand why not 5 but 4 options, 4 sec blocks will be supported? Because we just, don't go on writing anything. We know in our head that these are the sec options, but the system doesn't know. We need to tell that which option is that. So 4 sec blocks will be there. And if there are 4 sec blocks, then can you tell me how many losses are we indirectly indicating? Four. Okay, you are saying 4. So let us think about that. 1, if it is duplicate acknowledgement, that means right after this 1 is dropped. So that is by 1. 1, 2, and 3. Like there is one gap here, one here, one here. So 3 are indicated by this and 1 by the virtue of duplicate acknowledgements. You should be able to indirectly point to 4 losses as you have rightly said. So now I think we are getting too deep into this and we'll stop it here not the class, but about the selective acknowledgement options. Feel free to ask me if you have any doubts on this. Okay, so very quickly let us summarize this in the form of table. It is known as acknowledgement clock congestion window. Based on the acknowledgement arrival, congestion window will be improved. Why do we do that? To smooth out the packet burst. Like we don't double it and then send those many packets at a time on the network. But on arrival of each acknowledgement, slowly we are increasing the congestion window to smooth out the packet burst. In the slow start, we are doubling that. Why do we double it? To roughly reach the right level, because we have started just from 1. So rapidly we are increasing it so that quickly we can reach to the right level. However, there is a danger in doing it. So we enter into linear rise or additive increase, where we slowly improve. The purpose is same, to reach the right level. We don't, jump that. We don't cross it. Here, the fear was that we need to do that quickly. And now here, that we should not introduce congestion in the network. We should not send too much of data so that network will be congested. And for that, we are doing it. And purpose of this two mechanism is to recover from a loss without stopping for the acknowledgement clock. How without stopping the acknowledgement clock? Because if your congestion window is going to be 1, then acknowledgement clock has indirectly stopped. But we are making it half so that gradually you will be getting the acknowledgements and will be in the loop. So now we have already talked about this, that whenever there are wireless links, we have not exactly talked about this, but you are aware of this, that whenever there are wireless links, then packet losses might be there due to transmission errors. It need not to be the case of congestion always. If it is wireless link, then our data can be lost because of transmission errors also. Checksum will not match in that scenario. So it is a wrong packet, wrong data, receiver will reject it and no acknowledgement will be sent. So we should not confuse this loss with the congestion. Otherwise, we will keep reducing our data whenever there are random errors, and each time your transmitter will run slowly and efficiency will be compromised. So now we are taking one situation. There is a sender, there is a receiver. And our network is like this. That first part is the wired network. There might be 5 routers in between. But first part is the wired network, wired link. And then we have wireless link. The last hop is the wireless link. They are connected by a base station. This is a base station which is getting data from this part and it is forwarding data to this part. So if the network is exactly like this, that first we have wired part followed by wireless part, then we can do something to minimize the impact caused by losses over the wireless link. What can we do? Sender is sending data, base station will store it. And it will send the acknowledgement to the sender that yes, data has been received. So in this part, if everything is well, like if bandwidth is proper, you are sending data according to that, acknowledgements will be generated by the base station itself. And sender will be keep sending data at the same rate. Now, base station takes over and it sends data to the receiver. If it is not getting acknowledgement here, then we know that this is the wireless link. So there are very high chances that packet losses are because of transmission errors. So whenever it doesn't get an acknowledgement, what it will do? It will simply send the data. It will simply send the data. Flow will not be reduced. So what is the advantage? Without hampering data rate at the transmitter, we are able to maintain the speed, and this will be attempting retransmission locally in the wireless link and data will be delivered. Efficiency will not be compromised. In the normal scenario, if it was not done, what will happen? the sender will be sending data to the receiver. If receiver receives that, it will send the acknowledgement. If receiver does not receive that, no acknowledgement will be sent. So due to absence of acknowledgement, your sender will be reducing the flow. But that was not required because there was nothing wrong over the wired link. The problem was over the wireless link due to errors. And if it is a case of errors, retransmissions are sufficient remedy to recover from the losses. We don't need to reduce the flow to reduce the congestion. Do I have your attention? Are you with me? Nice. So this is known as split TCP, where we are splitting the TCP connection into two parts. So the obvious criticism for this is that TCP is supposed to provide you the end-to-end semantics. We are breaking that here. That is the first criticism of this. That we said that your transport layer should be running only on the transmitter and receiver. While here this intermediate node who is acting as if he is the receiver and then sending acknowledgements on behalf of that. What if the data would not be delivered to the next link? Then here your sender is in the illusion that data has been delivered. While here if there was very high error rate and if you could not deliver the data, then you are making your transport layer unreliable. So that is the criticism for this. And Hari Balakrishnan from IIT has suggested a solution to this. That semantic would be broken, but however, we can overcome the case of unreliability. Can you tell me what he could have done? What he would have suggested? He has just, tweaked the sequence of the actions. That is a very elegant and very simple solution. So what he said is that in the original one, the base station is getting the data and it is sending the acknowledgement. And then it is sending data to the receiver. He said that whenever base station is getting the data, rather than sending the acknowledgement, send data to the receiver first. When receiver gives you the acknowledgement, then only send acknowledgement to the sender. So the sequence was like this, that this is 1, then 2 acknowledgement, 3 data sent, and 4 acknowledgement from the receiver. He said that don't do it. From the sender, get the data. This is 1. Then send the data forward 2. 3 is get data from the receiver. That is acknowledgement. Get acknowledgement from the receiver. 3. And the 4th is to then inform the transmitter that data has been delivered. So if there was something wrong here, then local retransmissions will be done just like the earlier situation. But sender will not be notified about acknowledgement without actually delivering data to the receiver. Have you understood this? And in case, see, if there was congestion over the wired link, then what will happen? If there is congestion over the wired link, then no acknowledgement will be sent to the sender. And if sender does not get an acknowledgement, then sender is going to reduce the flow. So this works just fine. That if wireless link is having any problem, then this one will be retransmitting that without reducing the flow. If there was something wrong here, data will not be delivered, no acknowledgement will be generated, and the sender will be reducing the flow, which is required because there was something wrong over the wired link. And wired links are quite immune to channel errors. So if there is something wrong over the wired link, then there are chances that it is congestion. And if it is congestion, we want to help relieve network from that. So flow will be reduced. But there is another limitation of this is this particular mechanism will work only if the arrangement is like this, that first we have wired link and then we have wireless link. If it is first wireless link and then wired link, or first wired, then wireless, and then again one part of wired link, or something like that, in the heterogeneous network, it might not work. If you are well aware that this is the arrangement of the network, then only the solution can be applied, not otherwise. So I think we can end it here. So this is just the same one, splitting TCP in the two connection. There is a sender, TCP1 is running here and TCP2 is running here. Just another representation of what I have talked about. I have given here. This is splitting TCP or So if you have any doubt, you can ask me. Otherwise, we can end it. So I would advise you to go through this, and if you have any doubts, you can ask me. In the next class, will be concluding the transport layer. Mostly, we'll be concluding the transport layer, and then we'll talk about a few protocols of the application layer. Some protocols I'll talk about, and some protocols Sheetal Madam and Shefali Madam will talk about. So can I end the meeting now? Thank you.